So, hi. All right. So yeah, thanks for having me. So let me begin with a quick agenda for the next hour, right? So I'll be talking about modern Bayesian experimental design, which is more or less based on a review paper that we put out last year. And we'll be covering, roughly speaking, 3 topics. Number 1, variational Bayesian experimental design. Number 2, policy-based Bayesian experimental design and what we call the deep adaptive design framework. And in the third part, we will kind of go beyond parameter learning. Hopefully that will become clearer as we go. And there I'll actually talk about some a newer piece of work titled "Is Merging Worth It?" Which just got accepted at AI Stats this year. And as I said, if there are any questions, please feel free to interrupt. All right, so let me just motivate very quickly, what is experimental design and why we care about it. In general, many problems can be cast as a form of experimental design type of question. So, for example, if you're running an online survey, you may want to ask what the next best question is to ask a participant so that you can tailor your questions to the specific subject that you're interacting with. If you're a pharma company and you're designing drugs, you may want to know what the most promising compound to try for with specific characteristics is. And even when you think about active learning, what is the next best document to annotate, right? When annotations are very expensive, you may want to be careful about how you select the data that you annotate. And to kind of have a very simple example, as we go throughout this talk, I'll work with this sort of subjective time value of money experiment. So imagine you're a psychologist or behavioral economist, and you're trying to uncover people's underlying subjective time value of money preferences. The way that we normally do this is by asking participants a series of questions of the form, do you prefer some money now or some money later? And here I have 2 examples. The first one, do you prefer 150 pounds now or 100 pounds in 1 year? And the second one, do you prefer 50 pounds now or 100 pounds in 1 year? And intuitively, the first question is a bad question, right? So this is a bad design to ask a human being, a human participant, simply because, nobody will prefer less money in the future, right? So, asking this question will actually not give you any information about the underlying preferences of people. Whereas at the same time, if you ask, would you prefer 50 pounds now versus 100 pounds in 1 year? If you ask a poor graduate student, they may prefer the money now. And if you ask, an IT professional, they would they might be willing to wait a little bit longer. Now, the way that we're going to quantify this sort of underlying, which experiment is actually better, is that we're going to take an information-theoretic approach to this data acquisition. So we're going to be choosing the design so that the data that we collect at the end of the experiment will be maximally informative about some underlying quantity of interest. And let me introduce some notation here. The design that the design that we'll be choosing will be denoted by xi. The data that we collect will be denoted by y, and the quantity of interest will be a parameter in an underlying probabilistic model. And to just kind of put things into the familiar picture, we are going to work with a probabilistic model over our outcomes and the parameters of interest given the design. And in the traditional Bayesian way, we're going to have our posterior, which is proportional to the prior on the parameters of interest times the likelihood. Now, going back to our example, right? What is the design in this case? The design will be the tuple of the reward now and the delay in days. So this is just the tuple R comma D. This is our design xi. The outcome y will be whether the human participant accepts or rejects the delay. And theta is a parameter of a model that has this form, right? I mean, the form itself is not particularly important. It's a very simple model with a 1 parameter that we sort of want to infer from these questions. Now, what do we mean by maximally informative? Now, the good news is that once we have this model, actually the notion of information comes very naturally, right? So the obvious thing that we can look at is the information gain, which is defined as the entropy of our prior. And we compare that to the entropy of our posterior, having observed, having performed an experiment with design Xi and observed an outcome Y. Okay, so far so good. Now, in order to use this as a ranking metric before, in this case, we need to have the outcome line to actually compute the posterior. And as good Bayesians, what we're going to do is simply take an expectation with respect to the marginal distribution of this outcome. And this gives us the expected information gain. Okay, so the EIG is the expectation with respect to the distribution of Y of this information gain metric. Now, this goes back to Lindley, so this is nothing new, right? So this is, very well established. The problem, however, is that this sort of expected information gain is super nice to work with mathematically, but computationally, it has been pretty tricky to get it to work. And the reason for that is this sort of what we call doubly intractable objective, right? So the EIG is exactly equivalent to the mutual information between our parameters and our outcomes under the design. And you can do the KL gymnastics and get to all of the different forms of this expression, and whichever you choose, you end up with something that is intractable, right? So it's an expectation, and inside the expectation, we either have a posterior, which is typically intractable for most models, or this marginal in the denominator, which is also typically intractable for most models. So as a result, this EIG is super hard to work with computationally. It is hard to estimate, as we sort of generally require nesting of Monte Carlo estimators, and it's even harder to optimize. And typically what has been done in the past is running some form of either heuristic sort of random search or grid search, or gradient-free Bayesian optimization. Now I'm going to talk about variational BED. And kind of the key idea here will be to approximate some of the unknown densities, right? Either the posterior or the marginal, using specialized, highly expressive neural networks. So this is the general idea. And to kind of give you some intuition how it is going to work, let's take the EIG in sort of this form, right? So this is the expected information gain written as an expectation of the log density ratio between our likelihood and the marginal. And if we want to estimate that with sort of simple Monte Carlo, we can approximate the marginal in the denominator with another sort of Monte Carlo estimator. And therefore we see how this, we get this nesting of expectations, nesting of Monte Carlo estimators, which gives us a pretty poor convergence rate compared to kind of the traditional Monte Carlo approach. And also because of this log here that we have, we end up with something that is biased. The good news, it is asymptotically consistent, but nevertheless, for finite samples, it can be quite biased. So what we're going to do, rather than recomputing each of the marginals for every outer n sample, is that we're going to treat this problem as a sort of stochastic regression and learn a functional approximation to the marginal distribution, like this here. And we're just going to evaluate this function that will give us an approximation to the marginal, right, to the marginal Y. Now, the cool thing is, if we parameterize our functional approximation as a valid normalized density, what we end up with is a variational upper bound on the EIG, which is tight, if and only if this approximation actually recovers the true marginal, right? This gives us kind of the usual Monte Carlo convergence rate of square one over square root t, but generally it remains biased, right? So unless we actually recover the true marginal, there is no guarantee, regardless of how many samples we actually draw, that will converge to the true expected information gain, to the true mutual information. Now, And typically when I kind of give these talks to people that really do kind of serious Monte Carlo methods, the first thing that they complain about is that, oh, it's biased, this is very bad. And what I'm going to argue here is that, yes, it is bad, but at the same time, there are very easy ways to also get a variational lower bound and therefore sandwich our expected information gain so that you can actually sort of figure out how bad the bias might be. Right, so if we are approximating the marginal, as we said, we end up with something that is a variational upper bound. If we approximate the posterior instead, we end up with something that is a variational lower bound. And as a result, as I said, we can actually tighten, by either training more or coming up with more expressive formulations of our Q family. We can really sort of try and tighten these bounds and get to something that is pretty close to reality. Okay. So what we've done so far is that, as we said, these variational approaches will converge with the standard Monte Carlo at the standard Monte Carlo rate. So we can actually estimate the EIG efficiently for any given underlying design psi. But don't forget that we actually want to maximize the expected information gain. We don't want to just estimate that, right? So how are we going to do that? As I said, historically, people have done some form of Bayesian optimization, or you can do some form of a grid search, and so on. But now the cool thing is with sort of this, I guess, increase in popularity of differentiable simulators, is that we can set up unified objectives that will allow us to jointly estimate the expected information gain and also optimize that. So in particular, if, as I said, we have a differentiable simulator, we have a differentiable model, what we can set up is a variational lower bound to the expected information gain and maximize it jointly with respect to the variational parameters, phi, and the design psi. So that was done quite a few years ago now, and I would say that this is sort of the standard way of approaching design of experiments in at least with differentiable simulators. So sort of to come back to our example, right? So what we have achieved is that we can pretty efficiently ask the first question, right? So we can pretty efficiently come up with the first question in our sort of series of questions to determine the subjective time value of money, right? So would you prefer $49 now or $100 in 3 months, being the first one, to which the human participant says, I would like the $49 now, please. Now, what we're going to have to do next is, compute our posterior, and then we'll have to maximize our expected information gain lower bound, which we just discussed. It is very efficient, but we'll still have to wait, right? And this is what we mean by what we call traditional adaptive Bayesian experimental design, right? So the traditional approach to designing experiments would follow this loop iteratively, where after observing our outcome, we're doing a posterior update, and then we're using that posterior as a prior and essentially optimizing a new expected information gain to obtain the next design, and then we repeat. Okay. Now, yes.
Maybe go back to the maximization problem we have. Isn't that is always the case that the Latin function is jointly concatenated
No.
Psi and psi? But in previous.
Yeah, it's not. Yeah, it's definitely not the case. We are doing stochastic optimization, and we're kind of hoping for the best.
Global.
Pardon?
You mean global?
Well, we hope for a global, but we're using local methods, so you would be guaranteed under assumptions again that you'll converge to a local optimum. But generally speaking, if your problem is non-convex, then yeah, you can't necessarily get to the maximum, right? Yeah. right. So we're at the, we're repeating this this design of experiments in a loop, right, for t iterations. And as I said, we have our first, this sort of two-stage procedure where the first step is estimate a posterior, and the second one is compute the EIG, optimize the EIG. Now, obviously, both of these things are pretty expensive in practice. And again, when we think about our example, we don't necessarily want to ask the participants to sort of wait for 5 minutes for both of these steps to be computed. And the way that we sort of addressed this a few years ago now is by kind of taking a step back and almost rethinking this whole process of sort of the experimental design process itself. And this is what we're going to get to, right? So our proposed solution is what we now call policy-based Bayesian experimental design. And what we're doing is we're shifting the expensive computations in an offline pre-training stage, right? So in this offline training stage, what we're going to do is take our model, right? So our prior and our likelihood. We're going to roll many hypothetical experiments with that model, and we're going to train a policy that we can then deploy during the live experiment for very quick and adaptive design decisions. Now, what is this policy? So this policy is just going to be a function that takes our past data and it will output our next design. And to just sort of highlight that the traditional approach that I just described is actually a special case of this policy-based process where, the traditional BED approach is the two-stage expensive implicit policy, where the first stage is, as we discussed, estimate your posterior, and the second step is maximize your EIG. Now, what we're going to do instead of this sort of expensive implicit policy is that we're going to parameterize an explicit policy with a neural network, and we're going to use our past data. We're going to use our simulated data to sort of train this neural network. Okay. And the way that we're going to do that is essentially what we want out of this neural network is to amortize or to emulate the slow adaptive experimentation, the slow sort of this implicit two-stage policy. So mathematically, what we want out of this is that the policy should maximize the expected sum of our incremental EIGs, right? So each step of the experiment, we are sort of gaining an incremental EIG, and once we sum them together, that will be sort of the total EIG of the T experiments that we're performing. Now, informally, what we can show is that this incremental EIG formulation, right? So where we're summing these incremental EIGs after each experiment is exactly equal to the total expected information gain from the prior to the end posterior, right? So this is the key sort of finding. Well, it's a pretty straightforward, I guess, corollary from the mutual information chain rule, but that really helps us define what we call an end-to-end objective that we can then train with stochastic gradients again. Right, so a little bit more formally, right? So what we call the total expected information gain is this sort of expected information gain from the initial prior to the end posterior, and you have a single expression for that, right? So we have a single expectation of the log density ratio, kind of the history that we have acquired to the marginal of that history. Now, as we said, this generalizes the traditional BED, and this provides what we call an end-to-end objective that we can optimize with gradients, right? So we have our model, right? So we have our prior, and we can sample a history using the current policy that we have. And inside the expectation, we don't necessarily, again, have the marginal distribution, but we just discussed ways to approximate that, and we're simply going to use those methods to approximate this marginal in sort of this in this adaptive design case. And this is basically what we call deep adaptive design. The DAD objective is precisely this total information gain. And if we assume that we have access to the likelihood, we can employ pretty simple, almost like nested Monte Carlo type estimators of this quantity, or we can pick and choose any of the variational approximations that we just discussed in the previous part. We also extended this to models that are sort of simulator based, i.e., where we don't have an explicit likelihood function. And the way that we do that is by kind of borrowing some ideas from the representation learning literature. I've included all the equations just for a reference. I don't think they're particularly insightful to sort of look at in too much detail, but sort of the important thing to note is that all of them are computationally tractable, that we can optimize, well, calculate and optimize with stochastic gradients. And so just to kind of come back to our example, right? So this time value of many preferences experiment. Here we have basically trained a deep adaptive design network that sort of does this, that implements this experiment in practice, right? And we can propose new experiments with a single pass through that neural network. Here I have sort of quantitative results for this experiment where we're sort of comparing to two other approaches that have been specifically tailored for this model. The first one is a heuristic approach that is more or less based on some form of a decision tree, right? So, you know, if you answer the first question in this way, then you should ask that other question. Again, this has been developed by actual psychologists that run these experiments in practice. And here I'm showing the lower bound and the upper bound on the expected information gain. And as I said, this sort of gives us a way to quantify how biased these things are. And as we can see, they are pretty tight, right? Sort of the top one, as I mentioned, the heuristic approach, it is very quick to deploy, right? It takes well under a second to run. Again, it's a script that you read off, and it achieves an information gain of about 3.5 nats. We're implementing the traditional kind of this slow adaptive experimental design approach that we described, where after each experiment iteration, we're doing a specifically tailored Monte Carlo approximation based on population Monte Carlo. And that achieves much better performance in terms of expected information gain, but it is considerably slower to run. So although this is like very much tailored to this experiment, it is pretty considerably more expensive than a heuristic one, and also compared to our approach. And the weirdest thing was that the deep adaptive design approach actually performed better than the traditional approach. And this is really weird if you think about it, because we said that we're sort of approximating or we're emulating the traditional approach. So how come we're actually performing better than this much more expensive procedure? And if you were careful, there well, two reasons that I can sort of think of. The first one is that, in a sense, avoiding direct Bayesian inference can be a good thing, right? So we have this kind of T-step loop where at every step we might be making a small mistake. For instance, right, if your posterior, if your MCMC hasn't converged to the correct posterior and so on. So by avoiding this direct Bayesian inference, you're limiting error propagation. And it turns out that, generally speaking, it might be easier to learn to map from past data straight to next design, as opposed to going through a posterior approximation and in sort of this EIG optimization. And the second, actually bigger reason is that we're learning what we call non-myopic policies, right? So as I started saying, you know, if you were careful in sort of the definition of our objective, we're not optimizing for the next best design. What we're doing is we're kind of planning ahead and designing for the entire duration of the sort of the T experiments as opposed to for the next best. Right, so this non-myopic aspect is something that also brings us potentially a much higher information gain. Yes.
So on slide 40, the stuff you run this on, is this like this is a well-specified model?
Yes, this is a well-specified model.
I think this is sort of a very important part of the explanation and why it's performs better. So David Fraser works on these neural estimation techniques.
Yes.
For simulators.
Yes.
And there, and I imagine that this phenomenon carries over. You basically get an overfitting effect, which is a real problem in misspecification. Which is why I know about this.
Yeah.
And so I imagine that if your model is well specified, you basically just, you're hyper efficient, but you pay a cost, and the hyper efficiency is you also hyper non-robust.
Yes. I'm not sure if people online could hear that, but essentially the question is this a well-specified model? The answer is yes, this is a well-specified model, and what things will break down if the model is misspecified, and this is 1000% correct. And I agree with that. And my response is that we can actually extend this to running non-myopic policies at each experiment iteration and sort of combine the traditional way of doing this sort of computer posterior learner design, but in this case in sort of the combination with a policy, we can again computer posterior and then learn a new policy, right? And so actually this is what we do in another follow-up paper that we call stepwise deep adaptive design, and indeed that really helps if your model is misspecified.
I mean, my point is more that even the traditional version will suffer a lot under misspecification, right? It's just more pronounced what DAD does.
Yeah, for sure. Well, and I guess it depends what you mean by misspecification, right? If it's if your likelihood is wrong, then I guess if your prior is just a little bit off, right? Then
talking about
right. Yeah. So for sure.
When you say you're exposing to expected total information gain for capital T question, is there a way then also to optimize for that capital T, or is that something which
the question is there a way to optimize for capital T? And this is something that I'm actually currently thinking about, right? Because what you actually want to take into account is sample size requirements. Right? Maybe you're in a model discrimination setting. You kind of want to know, okay, how many samples do I need, for instance, to be able to discriminate between two models, right? Or even if you're doing parameter learning, it's like, okay, I want to make sure that my error bars are within some predefined term, let's say, right? So I think this is a very interesting thing to think about, but it's we're not dealing with this in here, and we haven't dealt with that yet. But it's a great question. Thank you. Great. Anything else? Nice. Okay, so we just discussed, right? We're learning non-myopic policies. So that was the first experiment. Here is another sort of quick experiment where we're aiming to identify the two hidden sources. Again, everything is well specified. You should probably start with that as well. And we're showing, the policy that has been learned. Essentially, it starts sampling, and once a source is located, it sort of samples a few more to sort of kind of get the location more precisely. And again, indeed, we're doing much better compared to kind of more traditional approaches. Now to kind of sort of repeat myself, the reason why this works better in the well-specified model case is that we're not doing this posterior estimation that may propagate errors throughout the sequence of experiments, and because of this non-myopic property. If there are no more questions, I will move to sort of beyond parameter learning, right? So far, we have primarily talked about learning the parameters of an underlying model, and there are many cases where we actually don't care about the underlying parameter, right? We may care about a subset of the parameters, or we may care about some form of downstream decision making. So how can we apply the setting in such cases? And I want to talk about sort of this paper, as I mentioned, that will be presented at AI Stats later this year, called, actually it's a much longer title than what I initially put, Is Merging Worth It? Securely Evaluating Information Gained for Causal Dataset Acquisition. So let me first unpack that. So what do we mean by merging, right? So we'll be talking about data fusion. Now, to kind of again give you a concrete example, think about a pharma company that has run a clinical trial in hospital A for maybe some rare disease, right? For a drug for a rare disease. Now the hospital wants to run a second trial, maybe because it didn't get enough power for their calculations. The hospital wants to run a second trial at one of K other possible hospitals. And the question is, which hospital should they choose in order to get the most benefit, or in other words, get the most information? This is what we mean by merging, dataset merging, or data fusion. Right, so we'll be acquiring a dataset, so we'll be picking the one that maximizes expected information gain. So we know what expected information gain is, and how to calculate that. What do we mean by causal, right? So we want to improve estimates of treatment effects specifically. We don't want to learn about all possible parameters that we have in the model. And finally, we want to guarantee that no information is leaked, right? You don't want clinical records to be distributed between hospitals or various institutions. Okay. So this is an overview of the method. We're going to have what we call a host institution or a host site, right? So this is the main hospital. The hospital has already run the clinical trial. The host will define a probabilistic model, and they're going to define their prior over the parameters in this probabilistic model, and they can fit their posterior with the data that they have. Then we're going to have K candidate sites. And all of these candidate sites will know what the underlying model is, right? So the probabilistic model is, or the form of the probabilistic model is known to all of the participants in sort of this setting. And we want to guarantee secure communication about among all of the parties, right? So the host will want to securely communicate information about its posterior to the candidate sites. The candidate hospitals or sites will want to compute expected information gain, given their data. And then they would want to securely return that EIG to the host so that the host can, make an allocation decision, right? So which hospital to invest to run the second trial. Is that more or less clear? I think there are a few moving parts. So yeah, okay, great. Yes. So. Sorry, I can't hear you.
Oh, sorry. What is data?
Oh, these similar as before, these are the parameters of our probabilistic model. Yeah, exactly. So that would be, if you're doing a linear model, these would be the parameters in your linear model. Yes.
Just to ask, candidates are also like K hospitals mentioned.
Yeah.
And in this case, we can all have the same distribution.
We'll get to that in the next slide. Yeah. Yeah, like it is the next slide. So this is our assumption on the generative process, right? So we have a bunch of covariates that we call X. The outcomes again are denoted by Y. T is the treatment effect. Is the treatment variable, and we're going to assume a binary treatment variable. And E is the environment, right? So E would be the different sites. Now, the treatment allocation schemes and the covariate distribution can vary across the environments, but given X and T, given the covariates in the treatment, the distribution of the outcomes will be fixed. Did that answer your question? Okay, great. Okay, so this is our setup. we're going to have again our generative process, right? Sampling from the prior and sampling from a likelihood. We will specify the likelihood in the next slide.
Quick question. So just double check the cosine and p. This is the joint p represent.
Say that again?
Because in the previous I'm saying the cosine and p. The p you said is the joint p of the ext and y.
I mean, the joint will be just multiplied the prior times the likelihood.
Oh.
Yeah, thank you. Right. So the goal for this exercise will be to estimate the conditional average treatment effect, or CATE for short. And for the people working in in causality under standard assumptions, the CATE is identifiable, and it's given by this difference in expectations, right? The difference in expectations given treatment equal to 1 and the treatment equal to 0. So between treatment and no treatment. This is what we're interested in making inferences about, not necessarily the entire parameter setup. So for the purposes of this work, we're assuming continuous outcomes and a normal likelihood, right? So the likelihood will be given by this form, right? So the mean will be parameterized by this f that we have, and we'll have some fixed or learnable variance. In this setting, our estimate for the CATE will be simply, the expectation. This expectation here between the means given treatment and no treatment. And again, if you're working in causality, you would know that many causal inference models decompose the parameters into something that is directly affecting the treatment effect and other nuisance parameters. So in a way, we can split our parameters into this set of non-causal parameters and causal parameters. As an example, you can consider Bayesian causal forests, where this mean is decomposed in this way, right? As one example. Now, the metrics of interest to begin with is going to be the expected information gain about the causal parameters, right? We want to make sure that we're learning the causal, or the parameters that the treatment affects as well as possible. And therefore, we're going to define kind of a more specialized expected information gain, where we're integrating out the nuisance parameters, right? And we're targeting information about the causal parameters only, right? And this is the formulation of the mutual information in this case, right? It's the same thing as before. It's an expectation with respect to the joint of the log density ratio of the likelihood to the marginal. We're also going to be computing what is called precision in estimation of heterogeneous effects. You can think about it as the mean squared error between the true and the estimated CATE. And again, this is sort of standard in the causal inference literature. Now, how are we going to guarantee privacy? Broadly speaking, there are a few ways that you can immediately think of, right? So number one is differential privacy. Maybe some of you are familiar with this, where the high level idea is that we're going to noise the inputs. We're going to have a statistical privacy, right? This is not cryptographically, you don't get cryptographic guarantees, you get statistical guarantees. In your balancing privacy versus accuracy, right? So you have this trade-off. You have fully homomorphic encryption, where the high-level idea is that you're performing all the computations directly on encrypted data. This is great in theory, but it doesn't really work for anything that is slightly complicated. So that's impossible for our purposes. And finally, we have something called multi-party computation, where the high-level idea is that you're going to share portions of the data across the different parties, and that will allow you to perform collective computations. And the kind of the core here is that you will be following a secret sharing protocol that basically gives you cryptographic security guarantees. So we'll be focusing on, we'll be using multi-party computation. We'll be comparing to differential privacy. And the reason why we're doing MPC is that indeed adding the noise at the very end rather than at the input stage, it will really bring your accuracy to a level that is actually acceptable. Does anyone know what MPC is? No, okay. So I'll give you a quick example. So here is an illustrative example of what multi-party computation is. Suppose we have 3 people, Alice, Bob, and Charlie, and we want to compute their mean salary. So Alice has a salary of 200K, Bob of 180, and Charlie of 210. And what we're going to do is that each person will split their salary into 3 random components, right? So that the 3 numbers will add up to the salary. So Alice is splitting her into 50, 120, and 30. So the sum is 200. And similarly, the other two participants will also split their salary in this way. And what they're going to do then, right? So you split your salary and then you distribute the chunks to the rest of the participants, right? So you keep one part for yourself, then you distribute the other parts to the other participants, right? So for instance, Bob tells Alice the number minus 80, it keeps 200, and then tells Charlie the number 40. Now, what everybody is going to do is they're going to add the 3 numbers that you get, right? So we're summing across the is it the rows? Yeah, whatever. You're summing across the rows. You get these 3 numbers, right? 70, 300, and 200, which you can communicate freely with everybody else. And then you can average that and get to the average without having revealed your salary, right? So this is the simplest case. There are protocols for basically every function that you can think of. They become much more complicated. And you're adding some bells and whistles on top to make sure that what we call this semi-honest setting, where everybody involved strictly follows the protocol, but they might try and infer some of the information, right? So even when you look at multiplication, you already have to add some extra security guarantees, because if you start making some computations, you can reverse engineer some of the numbers. So this is the basic idea. You're sharing chunks of your data with everybody involved, but they're guaranteed that they cannot reverse engineer any of the underlying input data. Okay. Is that more or less clear?
I feel like I've seen that before.
Did you say homomorphic secret sharing?
It's okay.
I don't know. So to my understanding, homomorphic encryption,
It's not homomorphic encryption.
No, that's not what it's about. Well, I mean, I guess you can combine the two. I think there are ways to combine the two, but I'm definitely not an expert. And so as far as I know, there are ways to combine the two and actually make homomorphic encryption actually semi-practical via this. Yeah. Okay. So this is MPC very briefly. So as I mentioned, we can follow various protocols for all of the operations involved in the computation of our expected information gain. I guess and again, these things are established, right? Like we haven't introduced a new protocol or anything. I guess the one thing that we sort of had to think about is the computation of the log determinant, right? So we have a bunch of normals, so that the expected information gain boils down to a bunch of normals, and you have a lot of things in closed form to sort of avoid taking square roots, which makes the computation much more expensive in this MPC scenario. We actually implemented a Cholesky LDL in the software that we're using. It's called Krypton, if you're interested, to compute log determinants more efficiently. And so here is a quick example. We have a synthetic experiment where we're doing a simple linear model with k equals 2 sites. And the 2 sites will be, number one, what we call a complementary data set, and the other one will be called the twin. So the complementary will be the ideal merge for causal purposes, simply because the complementary data set will be set up so that it complements the host, and you basically recover the entire RCT, randomized controlled trial population. The twin data set will be essentially the same as your host, i.e. drawn from the same distribution, and it will not recover it will not recreate the entire RCT. Now we're going to vary the ratio of the data set size, the twin data set to the complementary data set. And this is sort of the picture that we get. So let me walk you through that. On the x-axis, we have the ratio of data set sizes. On the left y-axis, we have the difference between the EIG for the complementary versus the twin. Anything that is above the 0 line will favor the complementary data set, and anything that is under the 0 line will favor the twin data set. So essentially what we can notice here are 3 regions. Oh, sorry, and on the right, we're showing the difference between the mean squared error between the complementary and the twin Kate estimates, right? So anything that is, as I said, anything that is below here will favor the twin data set. And indeed, in region 1, both EIG objectives. So the first EIG objective is just targeting all of the parameters in our model. They will favor the complementary data set, i.e. the correct one. In the second region, where we have more samples in the twin data set than in the complementary data set, the non-causally targeted EIG will incorrectly switch to the twin data set, right? So we can see these 2 lines, the green one and the orange one, are below 0, whilst the causally targeted EIG is still above 0. It's still kind of picking the correct data set. And once we get to like high enough number of samples in the twin data set, actually it makes sense to, simply because you have way more data in one of the data sets versus the other one, it actually makes sense to pick the twin as this difference in MSEs basically shows us. And in region 3, again, both methods correctly select the twin. So this is kind of a simple synthetic experiment to kind of make sure that things more or less follow intuition. We then run a couple of experiments with sort of semi-synthetic data set, where we have k equals 10 candidate sites, and we vary the sample sizes between 300 to 500, and actually the sample size in our host is set to 400. What we care about is whether the correlation between the data sets ranked according to our expected information gain, either targeting the causal parameters only or targeting all of the parameters. So we want the correlation between the ranking from the objective and the true ranking according to the PHE to be as high as possible, right? So that we are uncovering the true actually ranking of data sets. And generally speaking, and again, we do that for a bunch of different models. So polynomial, sort of linear model, a causal Gaussian process, and Bayesian causal forest. And generally speaking, the objective function that actually targets the causal parameters performs uniformly well across all models. So, I mean, it's a table with a lot of numbers. It's not particularly insightful, but it does well, I guess. That's the point. And to just sort of touch on the privacy aspect of things, I promised you that we'll be comparing to differential privacy. So we're following the standard procedures on differential privacy for linear regression. So we're using the linear model, sort of the polynomial regression in, again, for the same data set here. And we are reporting the mean squared error between the privacy preserving expected information gain and the corresponding noise-free expected information gain, right? So we want low mean squared error. And indeed, with our MPC protocol, we get something that is very close to the truth. And with differential privacy, we get something that is pretty bad. Looking at the rank correlations, again, of ranking the data sets, we get pretty good correlation with our MPC protocol of around 0.8, and essentially zero correlation if you were to use differential privacy. So that sort of shows you why you wouldn't necessarily want to noise your raw inputs. Are there any questions on this part? All right. And I think that is pretty much what I wanted to tell you from a I guess, technical standpoint. And I just want to end with, I guess, a call to everybody who does not just experimental design, but also, I guess, anything that is kind of or I don't know, like involved in Bayesian modeling and kind of, yeah, I guess, Bayes and Bayes adjacent machine learning. I feel like, what we really kind of need in terms of future directions for, I'm talking about experimental design in this case, but I think this really applies for Bayesian machine learning more generally, is that we kind of want to think about how we can apply these things to more real world type applications. And one thing that is sort of lacking, I guess, compared to the more traditional deep learning community, I guess, is really easy to use tools for these things. Right, myself, I'm guilty of that. When I publish papers, I don't leave my repos in the best possible condition. But I think as a community, it would be great if we can strive towards, more unified tooling for both, things like experimental design, but also the modeling side of things, building differentiable simulators, and so on. And sort of, a crucial aspect of this, at least for experimental design, is working more closely with scientists and domain experts to actually define what models make sense and actually run these things in sort of real life scenarios and like real experiments. And with that, I think that is everything from me. Are there any questions or comments from?
One, the basic question earlier was about whether there's an interpretation for nouns.
Sorry?
For nouns, you were saying,
Oh,
for example, in the 3, would this correspond to, I'm thinking like in this case, conjugate exponential models, something you understand a prior as extra data points. You understand maths as extra data points or something like this? Is there some?
I don't know about it. Possibly, but are you talking about if you were to, I guess what I can think of is if you were sampling data at random, how much data you would need to achieve the same expectable gain in that one case or whatever. That's the kind of right what the function is versus how much data you need by this more careful data selection. And you can compare, right? So maybe price of function and time of function on the random sampling versus. But yeah, I'm not sure if that is exactly what you're trying. Yes.
Yeah, just on this last bit. So, what are practitioners currently doing? Are there some tools that exist, and are they anywhere near the level of?
Yeah, so I think for Bayesian optimization, there are a few really well-established libraries, things like Blowtorch, right? So that's Blowtorch for Bayesian optimization specifically. That's a team at Meta. They run huge number of experiments all the time, and they have a dedicated team to support that, which in that way, like, it's really good, right? If you work on data, like, they're having a good time. And using that, if you're working on anything else, then, yeah, there isn't much out there. Yes, exactly, yeah. And the team there is great, yeah, so, you know, Ethan,
You're right, it's a badge of honor. But that was slightly more conceptual, right? So on slide 10, you have this like difference in information, like the information game, right? Which is just the entity, you know, prior and the posterior. I was thinking about this a little bit because so if you're targeting this, so obviously I'm always worried about misspecification, and I'm obviously worried in that regard there. So you're basically getting the most greedy thing,
yes,
which is exactly the opposite of what you want to do. You're worried about the possibility. But even outside of that, are there situations where that thing is problematic, even if the model is well specified? Like I imagine if your prior is really poor, for example, you eventually want to shift your posterior to a different place.
Yeah.
The posterior could sit like the entity doesn't necessarily tell you anything about what that posterior is. It just tells you how concentrated that object is.
sure, yeah, for sure. But I guess you're assuming that you are getting the correct posterior.
Yeah.
So we're not assessing posterior quality
Yeah,
anyway.
yeah, yeah.
Like, and
Yeah,
yeah,
okay.
you should be assessing posterior quality with traditional tools for assessing posterior quality.
Yeah, but you're mapping the posterior into a scalar measure. Well, the entity, right?
Sure.
And then you're looking at the difference. I guess I'm wondering, are there any known pathologies? Maybe this is the question I'm trying to ask. Are there any known pathologies for doing this information gain outside of, like, let's forget about specification. Everything obviously goes wrong then. But even if your model is well specified, are there some pathologies I could encounter happen in this setting?
I think you should, I mean, I'm not sure what you mean by pathology, right?
Undesirable behavior. Like, what guarantees do I have if I use this information game?
Yeah.
That would be the opposite way of asking.
Yeah. So as far as I know, there is actually a theoretical guarantee. But okay, if you're in the well-specified case, I just don't. I haven't seen like the non-desirable behavior, or I can't think necessarily think of that. But even if your model is misspecified, there is a guarantee that it will converge to something that that makes sense, right? Let me try and remember that. If you're doing sequential updating, right? So you're fitting a posterior after each experiment. You will converge to the theta that is closest in KL to the true theta of the model, right?
It's super true value,
The
if
super
it
true,
exists.
right? Yeah. Yes, exactly.
Yeah, okay.
But generally speaking, as far as I know, there is very little theory done in this active data acquisition setting. And partly, it is partly because things can go very wrong, like extremely wrong. I think I have a quick example,
That would be
actually.
very good.
Yes, sure. So if you're interested in theory,
Yeah,
I think,
definitely. I mean, we talked about this before.
yes, it's true. Yes.
Now that you said it.
Yes, so here is a kind of a catastrophic failure. If you were to assume a linear model and gather data when the underlying true data generating distribution is a quadratic, right? So if you're in a linear model setting, you always sample at the edges, right? This is the thing that maximizes your mutual information. And in this case, you don't even have enough data to detect misspecification, right? And if you were doing random sampling, you would fit this model, which is actually closer to the truth, and you will be able to potentially detect some form of misspecification, right? so I don't know if that kind of
Yeah, I mean,
answer.
this part of the question, that makes sense to me. I'm basically wondering what the guarantees look like. But I think I just need to read you sent me a paper ages ago, which I still have to write. I need to read that and ask the questions.
I personally haven't done theory, and I think there is quite a lot of scope to theory, if that is what you're interested
I
in.
will have a chat on this.
Yes, let's do.
Are there any more questions for this? No, more questions are there. And we also have some biscuits upstairs anyways, so if anyone is too shy to ask now, you can also ask them. So let's thank Desi again.
Thank you.